Hello. In this video, I would like to tell about a Hystax Acura solution. We'll take a look at the components, their principles of work and interaction. And we'll take a closer look at the work of replication agents, which actually provide the ability to transfer machine data from the source cloud to the target cloud. What is a Hystax Acura solution? The solution is a unified technology platform for all three use cases that we provide with it: a migration, a disaster recovery, and a backup scenario. The main server part of the platform is a controller. It is a single or a set of few virtual machines that are deployed on the target cloud or target platform. It deploys from the image that we provide. If a controller is a single machine, it is called a single node controller. It can be used to provide small migrations. It might be a migration or a backup scenario for a single client, for instance. When I talk about small, I mean the amount of source machines. In case, if you need to migrate a large number of virtual machines or to provide a migration for many clients, or maybe you have a backup or a disaster recovery project for a large number of machines or for a large number of clients, then we recommend deploying the controller as a group of machines for high availability, as well as to balance the load between them. In this diagram, the controller is a single entity, and it doesn't matter for us if it is a single machine or a group in this case. So, the controller is located in the target platform. An operator interacts with it. An operator is a person or an automated system that gives tasks to the controller to perform some actions. To provide an interaction between an operator and controller, ports TCP/443 and 4443 must be opened. Port 443 is a standard port for HTTPS. It is used by the controller web interface and all the APIs provided by the controller in order to integrate our solution with your automation, monitoring system, or your control panel. The second port, 4443, it is used at the very beginning of work at the stage of initial configuration of the solution. The interface of the initial configuration is located on this port. Once the configuration is completed, this port can be closed, and port 443 remains open. Replication agents are deployed on the source platform. There are two types of replication agents: external and internal. Internal replication agents work inside of the machines they replicate. These are services that are installed inside of Linux or Windows machines. They run as a part of these virtual machines and replicate it. External replication agents work on the hypervisor level. They are not installed inside the machines that they replicate, but are installed next to them. This type of replication agents is currently available for VMware-based or OVERT-based source clouds. Replicate machines, external replication agents, communicate with hypervisors and the source cloud API. For example, in case of a VMware with the vCenter API. Replication agents interact with the controller. In our solution, this connection is established for over two ports. The TCP/443 port is mandatory. It's an HTTPS port. Via this port, replication agents reports their status to the controller and transmit data that is replicated from the source machine. The second port is UDP 12.2.0.1. This port is optional, but it's highly recommended to use in case of big projects for migration or replication. Using this port, replication agents transmit logs of their work to the controller. These logs are stored in the controller in the Elasticsearch service. This is convenient because later the operator can get an access to logs fast, and there is no need to connect to the source cloud. It might be useful in the situation if the operator does not have any access to the source clouds or source machines. Otherwise, he or she should ask a customer to provide logs from a specific machine. It might take a long time. A cloud agent is an auxiliary virtual machine that usually deploys automatically from a preloaded virtual machine image. This machine allows the controller to write the data transmitted by the replication agent in block devices in the target platform. This machine is used in the replication process in all scenarios. When I'm talking about scenarios, I mean a migration, a disaster recovery, and a backup scenario. Later, I'll tell you how it is used. A controller communicates with a cloud agent. It connects to a specific cloud agent instance via the TCP/80 port. The controller also requires an access to the target cloud API. Here, in the diagram, instead of the port number, you see an asterisk, which means that in this diagram we cannot predict which port will be used for the cloud API. This port depends on the type and the deployment characteristics of the target cloud. When a backup scenario is implemented, the controller requires an access to an S3-like or a file storage. In this case, the data is stored not in block devices on the target side, but in third-party storage. It gives us more efficient storage. As I mentioned above, there are two types of replication agents: external and internal. External agents work at the hypervisor level and are capable of replicating many machines at once by one agent. Internal agents are installed inside the operating systems and replicate the machine on which they are installed. To ensure replication consistency, all of these agents take snapshots on the source cloud. The type of these snapshots differs depending on the agent type and the type of source cloud we have. Let's take a look closer. A VMware agent is deployed as a virtual machine on the source VMware cluster and communicates with the vCenter API and with an API of a specific hypervisor in this cluster. Using VMware tools, it takes snapshots on the replicated virtual machines. So the replication begins and the snapshots are created. The cloud agent takes the data of the snapshots through the VMware API and transfers the data to the target cloud. On the target cloud, the data is being written to the storage. When the replication is completed, snapshots on the source machine are deleted. When the command on the next incremental replication comes and a new snapshot is created, the cloud agent connects to the VMware API and gets information about changed blocks of data compared to the previous snapshot. The solution transmits only these changed blocks on the target cloud, thereby ensuring efficient data transfer. An overt agent. Generally, the situation is very similar to the situation described above about a VMware agent. The agent is deployed as a virtual machine on the source side, communicates with the API of the site, creates snapshots of virtual machines, reads them, and transfers data to the target cloud for writing. What to do if it is impossible to use internal agents? For example, you use not a VMware or not an overt cloud. Or in case of a VMware, you don't have any access to the vCenter API. In this situation, it is recommended to use internal agents. A Windows agent works with a volume shadow service to create snapshots. A VSS is a standard local volume snapshot system in Windows. When the replication starts, the VSS creates snapshots that are used as a source of data and are transmitted to the target cloud. When an incremental replica is launched, a new snapshot will be created, and then a so-called change block tracking process will be created to find out what blocks have changed between the previous and a new snapshot. Unlike many other solutions, our replication agent does not use a proprietary Windows driver when performing change block tracking and does not require an installation of any additional drivers. We use our proprietary library to find out the blocks have been changed between two snapshots. This library can read data sufficient to find out the list of these blocks. We don't interfere in any way to the system and don't install any additional drivers. The solution works without them. There is no additional way to take snapshots from local block devices in Linux. In the Linux ecosystem, there are only certain cases when you can take a snapshot from the storage. For example, at the file system level for a Btrfs or at the volume level for an LVM. But neither Btrfs nor LVM have 100% coverage of the entire system. Here, the solution uses an alternative approach. It uses a proprietary driver that can take snapshots of local block devices and do change block tracking between two snapshots to find out what data has been changed. This driver is a kernel-dependent driver. Kernel support for this driver starts with kernel version 2.6.32 and is currently limited to 5.14. Work on support for 5.15 and higher is currently underway and will be available for use in the near future. There are two ways to download the driver. The first is a pre-built driver. The driver is assembled when we build a new version of the product and is attached to the replication agent install. The list of supported kernels can be seen here. The second way is the delivery from the source code using the DKMS system. It allows to assemble the driver directly on the machine where the replication agent is being installed. Once the options are selected, you are taken to a page that provides a link to download an agent installer. It can be used to deploy the replication agent on the source cloud. The agent installer already contains configuration information. So, when the installation is completed, the agent connects and registers on the controller and is ready to start machine's replication. In the vast majority of cases, there is no need in additional configuration of the replication agent on the source side. All you have to do is to install it and immediately start replicating machines. This allows you to download one agent for Windows or Linux and roll it out using automation tools on hundreds of machines without having to go to each of them to install the agent, to configure configuration parameters, and etc. Let's consider replication method without paying attention to agents. Let's look at the replication process from the infrastructure side. What operations take place on the target cloud? The simplest situation occurs when a backup scenario is implemented. No additional operations with the cloud occur. The data is transmitted by the replication agent and processed by the controller. The replicated data is stored in an S3-like or file storage. The data in these objects or files is deduplicated. No additional operations occur from the infrastructure. The data is simply being replicated. The storage is cost-effective. The situation differs when a replication is taking place into block devices. This type of replication is good for a migration or a disaster recovery scenario. It's a rather complicated process. Data is transmitted and recorded to the target cloud as blocks. The replication process can be divided into 4 stages. At the first stage, the controller checks that the cloud agent instance exists in the target tenant. This instance is a data proxy and it allows us to write to the block devices on the target side. If this instance does not exist or the amount of instances is not enough to ensure simultaneous replication of the required amount of volumes, then a cloud agent or an additional cloud agent will be created. There can be several cloud agents on the target cloud, and they are automatically created and destroyed by the controller if necessary. So, the first step is to make sure that there is a free cloud agent in the target cloud that can be used to write data. Let's go to the second stage. As soon as the cloud agent appears, a volume is created on the target side. This volume is identical to the volume of the original machine. It is large enough to hold all the data from the source machine. The volume size is rounded up to the nearest gigabyte depending on the target cloud. The solution takes into account the option when the volume allocation unit size of the source and target clouds is different. For example, for VMware it's 1 megabyte, but in OpenStack the volume allocation is 1 gigabyte. If the machine is migrated from VMware to OpenStack, then the volume on the target side will be larger than on the source side, but sufficient to accommodate all the data from the source side. Thus, at the second stage of replication, a volume is created on the target cloud. On the next step, the created target volume is attached to the cloud agent instance and becomes a local block device. The replication agent transfers data to the controller. The controller routes it to the cloud agent, and finally, the data ends up on the target volume. At the end of the replication, the target volume is a complete binary copy of the source volume. At the end of the replication session, the target volume is disconnected from the cloud agent instance, and a snapshot based on it is taken using the cloud services. This snapshot is a recovery point, and in the future it will be used to raise virtual machines on the target cloud during a migration or a disaster recovery process. On the next replication, the target volume will be attached to the cloud agent instance, and changed blocks of data will be added to it. After it is disconnected, a new snapshot will be taken. Several snapshots can be stored. If it is set in the settings that only one recovery point should be stored on the target side, then an old snapshot will be deleted. It was the fourth stage of the replication. Let's talk about a recovery process in case of a migration or a disaster recovery scenario. Let me remind you that in this case, replication occurs in a block device. Having received the command to restore the data, the cloud controller creates a volume from the snapshot via the Cloud API. A virtual machine is created from this volume. To do this, the volume is connected to the Cloud Agent instance, and a P2V or a V2V conversion is performed on the operating system inside this volume or volumes. The installed drivers are checked inside the operating system if it is available to boot on the new platform. The controller makes sure that it is ready to boot on the target site where we are going to run this virtual machine. It is checked that the bootloader of the operating system is supported by the new hypervisor. If necessary, the loader is adjusted so that the machine can load at the target cloud. This is useful. For example, a source machine is booted in a UEFI mode, but on the target cloud, this mode is not supported. A number of additional transformations is performed. Despite the fact that there are quite a lot of transformations, they are very quickly. The listed operations involve writing 100 or 150 megabytes of data into the operating system of the recovered volume. It takes constant time and does not depend on the size of the machine being restored. After that, the recovered volume with an operating system is disconnected from the cloud agent, and the controller creates a virtual machine from this volume, according to the parameters set in the migration or DR plan. As a result, on the target cloud, you get a virtual machine. It works well and can be used despite the fact that the hypervisor has been changed. Let's consider the recovery algorithm for the case of a backup scenario. Hold on a minute while I am getting it back. The main difference is that a block device must be created before a virtual machine is created and P2V and V2V conversion is made. The rest is actually the same. So the restored volume is created and it is attached to the cloud agent. The data from the restore points that are stored here is transferred to this volume. After that, P2V or V2V conversion is performed. This process is exactly the same as for the block devices. The restored volume is detached from the cloud agent and the virtual machine is being created. Thank you very much for your attention. I hope it was useful.